And our next speaker is Vitaly. And let's see. Oh, it's blocked. So this is a generalization between word vector sets. Okay. Let's welcome our speaker while he's preparing for the. Okay.
Hello, everyone. I'm Vitaly, and thanks a lot for coming to this talk about correlations between word vector sets. This is a joint work with April, Dan, Alexandra, and Nils, my colleagues from Babylon Health. And the code for this paper is available on GitHub. Also, we have this Python library with semantic similarity measures that I'm going to discuss, and many more, so check it out. Cool. So, when we talk about correlations, we talk about statistics, right? And when people try to bring statistics to word embeddings, they would usually do it like this. They would say, okay, so we have a word embedding matrix which lives in R n times D. And usually D is 300, and n can be millions, so like 2 million words, 3 million words. And each row of this matrix is a d-dimensional word vector. So we're dealing with a situation here that we have n observations from D random variables, right? So our rows are observations and our columns are random variables. And we have a probability distribution like this. There's a lot of things you can do with this. So we can fit a Gaussian, see how embeddings correlate, for example, or we can fit a mixture model, find clusters, or we can do PCA and just get the overall feel of geometry of the embedding space. And there is also sort of like a global similarity structure given by Mahalanobis distance or Fisher kernel, etc. So this view is very useful for overall geometry of the space. But there is a different way. Instead of looking at the matrix W, we can look at the matrix W transpose, which now lives in R D times n. And now we are dealing with a different situation. We have D observations from n random variables, like this. And what happens here is that each word Wi now has a scalar random variable Wi, big Wi, and word embedding Wi becomes a sample of 300 observations from that scalar random variable. And then the similarity between Wi and Wj is given by the correlation between big Wi and big Wj. However, of course, the theoretical marginal P Wi Wj is not known to us, but in statistics, we can make inference about this marginal based on our sample, our word embeddings. So yeah, this is sort of the previous, like the main idea of our previous work presented at NUCCL, that a word embedding is not a vector, it's a statistical sample of, for example, 300 observations from some scalar random variable. All right, so let's see how this works in practice. So we have these two word vectors, cat and dog, and I put a small number 300 to indicate they are like 300 dimensional. So in geometry, we care about cosine similarity, so the cosine of the angle between these vectors. But in statistics, we have histograms. So we can make a histogram for cat, we can make a histogram for dog, and in the middle, we have a scatter plot between cat and dog. And we're interested in the correlation between cat and dog, right? So notice how this is very different from geometry. Geometry gives us an overall understanding of the embedding space, but statistics is very targeted. It gives us a very precise understanding of the similarity between two words. In geometry, you can't really visualize 300-dimensional word vectors on their own, but in statistics, I just did that. So this is like accurate representation of these vectors, for example. So here are some histograms for a bunch of sort of random word vectors from different word vector models. Again, I was able to visualize them very easily. Right, so in geometry, we have cosine similarity, but in statistics, we have Pearson correlation. And it's not hard to see that they look very similar. The only difference is those mean terms here. But actually, it turns out that means not that important because for the models we considered, which are word2vec, fast text, and GLOV, they are tightly concentrated and symmetrically concentrated around 0. And we can sample a bunch of pairs and compare cosine similarity and Pearson correlation, and the difference empirically is not that big. So empirically, they're sort of almost the same thing. Okay, so if they're almost the same thing, why do we care? Why not just use cosine similarity and be happy? Well, Pearson correlation and thus cosine similarity are only sort of safe for a multivariate normal distribution. In a sense that for multivariate normal distribution, Pearson's R gives us all possible association there is. There is nothing else that Pearson R doesn't capture. But when the joint distribution is not normal, then Pearson R might not work at all. So we basically need to test our word vectors for normality. We can do this manually using QQ plots, histograms, and scatter plots. So on the right is an example of QQ plot. It's a scatter plot between the quantiles of standard normal distribution and theoretical normal distribution and our data. So we can see, for example, that word2vec is on the diagonal, so it seems like it could be normal. Fast text, the first one seems normal, the second one not so much, and GLOB is like definitely not normal. There are these massive outliers. So outliers in bivariate distribution is actually a big problem because a single carefully placed outlier can completely destroy the association. And this is especially prominent in GLOB vectors. So for these vectors, we can instead, and should probably instead, use more robust rank correlations, such as Spearman-Rho and Kendall-Tau. So you can see, again, for example, top right corner in GLOB, there is these outliers. The association is still linear, but the outlier can completely disguise that association from Pearson correlation. Cool. So this paper is actually a generalization of this whole business to the case of sentences. And there are two ways we can do this, using pooled random variables or multivariate correlation coefficients. So to briefly introduce our tasks, they are semantic textual similarity tasks. We have two sentences, a human score and a machine score, and then we compute the correlation between the human and the machine. So the correlation here is completely different from the correlations I discussed before. It's basically an evaluation metric, whereas before we talked about similarity measures between word vectors. And these tasks are like super popular. There are a lot of papers, and they seem to be gold standard in the STS literature. Okay, so a pooled random variable is nothing, but it is basically just we can take word embeddings and apply min pooling or max pooling or any other pooling, and we will get some other random variable, W pool. Luckily, this random variable is still a univariate, a scalar random variable, so univariate statistics still apply. Here are just some examples of min pooled sentence vectors, max pooled sentence vectors, and min pooled sentence vectors. Okay, so here's the analysis. So as the same in the case of word embeddings, we see that the first two bars are Pearson correlation and cosine similarity, which are basically the same thing. This is a simple consequence of the linearity of expectation, because we know that the means of word embeddings are 0, so the mean across the min pooled sentence will also be 0, or at least close to 0. However, when word vectors are not normal, such as GLOB, so for GLOB there are 97% of them are not normal, and for fast text about 96% not normal, Spearman and Kendall significantly outperform Pearson and cosine similarity. But for word2vec, most of them seem like normal. So there really is no difference for word2vec. You can use any of those similarity measures. It doesn't really matter. So we can also analyze max word vectors. In this case, it's fairly obvious that cosine is not going to be the same as Pearson, because the mean is going to be shifted to the right. Unfortunately, by construction, these vectors will not be normal at all, because they will probably have a positive skew. But max pooling has this interesting property that it seems to reduce the outliers, right? Because max pooling kills the outliers in the left tail and pushes the whole distribution closer to the outliers in the right tail. And it seems to be true here. So there is still a gap between Pearson correlation and rank correlations, but at least this gap is not as huge. Cool. This is just like a commercial break. So here we have a state-of-the-art comparison against deep learning representations, and we can see. So we have universal sentence encoder, InfraSend, BERT base, BERT large, Elmo, and GenSen, and we see that a simple average word vector, a simple average fast text vector, compared with appropriate correlation, in this case Spearman correlation, is competitive against all these deep learning models, while being obviously much, much simpler than deep learning models. Cool. So Pooled random variables are great. They are easy to understand, and they seem to work really well. But unfortunately, they're a bit arbitrary. There's no a priori reason why we should mean pool or max pool or do any other kind of pooling. So we can be a bit more formal, and we can just use multivariate correlation coefficients. So we're going to take a look at Pearson correlation and try to generalize it. So Pearson correlation is a covariance between x and y divided by standard deviation of x and standard deviation of y. And we're interested in this covariance term here. So instead of scalar random variables, we now have random vectors x and random vector y. And we can take a look at this cross-covariance matrix. A cross-covariance matrix is very easy to understand. The element Cij is simply the covariance between xi and yj. And then we can take one step further, and then we can pass this vector x through a feature map phi and vector y through a feature map psi, where phi and psi are associated with some kernels, k and l. And we get the thing known as Hilbert-Schmidt independence criterion due to Arthur Gretton and colleagues. The reason, so basically the cross-covariance operator here is an infinite dimensional operator, right? But we really need a number because similarity is just one number, and infinite dimensional operator is definitely not a number. So we simply take a Hilbert-Schmidt norm of this operator to get that single number. And in terms of kernels, it can be written like this. And the authors also give a very simple empirical estimate of this norm, where H is a simple centering matrix, and the kernels can be written like this. And the important thing to understand is that the kernels here take place not between word embeddings, so not between the purple embedding and the pink embedding, for example, but actually between the observations. So we'll take a dot product between first observation and second observation, first observation and third observation, first observation and 300s, and so on. And we will get kernels in R300 by 300. But remember, we actually wanted Pearson. We didn't want covariance. We wanted the correlation. So we simply just copy how it looks, and we obtain something known as centered kernel alignment due to Cortez and recently used by Kornbliss. And so the good thing about HSIC is that when K and L are characteristic kernels, HSIC can really detect any dependence with high probability as the sample increases, sample size increases. So it's time for showdown. So here we have a big table with all the popular methods. In the first section, we again have the deep learning methods, and in the second section, we have a very popular set-based approaches, and our approaches highlighted by a star. And we see that overall they are very competitive, even win on some tasks. And obviously they are much simpler than some of the competing approaches, right? So max pool Spearman is just a simple max pool vector compared to Spearman correlation. And CKA is slightly more complicated, but not that much actually. So here are some references to the works I mentioned. And thank you very much.
Questions from the floor? Okay, good.
Thanks for the talk. Have you tried using contextual word embeddings with the alternative correlation metrics?
That's a good question. I really have not looked at any of the contextual word embeddings, or I haven't even looked at the sentence embeddings from this point of view. That's definitely something to try. The theory there will be like a bit more complicated. It would not be quite clear what is a random variable. In other words, it's a random variable that keeps changing. So it requires a bit of high-level theory, I guess, to think about. But certainly, if those embeddings have the outliers, I would not compare them with cosine similarity because that outlier can hide the association.
Thank you.
Okay. Any other questions? Okay. Yeah.
Since nobody's asking, I'm going to ask a stupid question, but something that's bothered me for a long time. If I train, say, a Word2Vec lexicon, right, I get a certain set of embeddings. If I now retrain on the same corpus, again, the Word2Vec thing, and I just change the training order, right, I'm going to get a different set of embeddings, but it's the same thing. So I've often wondered, how different is different? Could I take your approach and instead of looking at all the rows, like all the words, I just look at all the columns, and then I can say, in set 1, I had one little column, one dimension, say dimension 5, that had a certain characteristic, and in set 2, I'm looking and I say, oh, here is dimension 72, and that has the same character. Could I go and do column by column comparison to discover whether the sort of Word2Vec embeddings learned under one regime the first time are in fact similar in some sense to the ones in the second time? Is that a stupid question, or is that a useful thing to do?
It makes perfect sense. So if you think of one word embedding, thanks a lot, that's a very good question. If you think of word embedding as a sort of sample of 300 observations, in statistics it doesn't matter in which order the samples come from. So you can shuffle them and you'll still get the same thing. So it might not be as easy as comparing, column in the old embedding to the new embedding, because you actually have to find the new column. But certainly, I would expect if you retrain them, these statistical regularities, like GloVe has a lot of outliers in them, will hold, and Word2Vec should not have more outliers. And in fact, it's true. I even trained Word2Vec on many different corpora, and this is a general property of sort of embedding model. It doesn't have outliers, but for GloVe, there are outliers. So. Yeah, it's certainly possible. It's difficult to reason about this than the first case you mentioned, because in the first case, when we have the other side of the matrix, we can do sort of the PCA, and we can do the rotation of one space onto another, and we'll see those regularities. Here, we can't really do PCA because we have less observations than random variables, so it's a bit difficult to do this rotation, but it could be possible to find the correspondences. I would need to think about this.
Okay, we still have time for one more question. Okay, good.
Hello. That was a great piece of work. Do you have any speculations for why GloVe has prominent outliers and Word2Vec doesn't? I mean, you could have thought that they should behave the same that way, though perhaps the kind of stochastic optimization of Word2Vec has a strong regularization effect or something. Have you thought about that any?
It's an excellent question. I personally haven't, but I presented a poster at NACL, and some person came up to me and he had ideas why that would be the case. So I'm stealing his ideas. He basically said that in GloVe, I don't remember exactly, but he hypothesized that in GloVe it's normalized along columns or something. And if that happens, that column, for example, might get thrown off. And in fast text, it's trained with subword information, but then these subwords are somehow removed from the vector. So he told me that these post-processing steps might somehow alter them. I'm not quite sure about that. I haven't personally checked if that's true. If that is not true, if there is no pre-processing going on, then I really don't know. Yeah, I'm not quite sure, because especially it's interesting, right? Because these word vectors optimize dot product, right? So do you think that dot product, cosine similarity, and Pearson are basically all quite related? So why would there be an outlier, and Spearman correlation would be better than cosine similarity? So yeah, I'm not quite sure about this. That's definitely a great question to answer. Requires more detailed analysis, I would say, of the algorithms and data sets, maybe. Mm-hmm.
Okay, well, let's thank our speaker again. Okay.